All right, so in the last class we were looking at the stack class, or not class, the stack data structure where we're implementing it using a bunch of linked nodes. The last thing, so I don't remember if I talked about this or not. I don't think I did. So when the user makes a stack, right, they call the init function. Right, in the init function, we allocate or dynamically allocate memory for the, sorry. Oh, that's not what I wanted to do. We dynamically allocate memory for the stack data structure, for the stack structure. Now, when we push elements onto the stack, we also dynamically allocate a node. So if you want to get rid of a stack, you need to get rid of the memory or free the memory that was allocated for each node, and you need to free the memory that was allocated for the structure. Now, the user of the stack doesn't know how to get to the nodes, right? So the user of the stack only ever sees the type def in the header file, which is here, right? So the user only ever sees the type def. They don't know what's inside of a stack structure. So it's up to the stack object itself to figure out how to free the memory it's using. So we need to provide a function that deallocates the memory for all of the nodes and for the stack structure itself. Right? So to free a stack, you need to iterate over the nodes. Right? And to iterate over a linked sequence of nodes, it's always the same pattern. Right? Start at the beginning node. So in this case, we start at the top node. While that node, or while the pointer to that node is not null. Right? Here I'm going to look at, I'm going to get the next node in the sequence first. Right? The reason I'm getting the next node in the sequence first is because I'm going to free the node in the next step. Right? If I free the node in the next step, if I free first and then try to get the next node, that doesn't work, because after freeing n is no longer a valid pointer. Right? And then move forward in the sequence. Right? So n now advances to the next node, and once you've freed all the nodes, you can go ahead and free the stack structure itself. And that completes the implementation of our stack structure. Now, what happens if you want a generic data structure? So our stack and our list, oops, sorry. This says queue, but we didn't actually do a queue, but you could easily do a queue given that you have the stack. They're all collections of ints, right? So we got a stack of int, we got a list of int. What happens if you want to make a stack or a list of something else, right? So of double or of strings or something, right? Then in C, you're stuck with this problem, or at least in our current situation, we can't do that easily. What we'd have to do is we would have to make a new data structure, right? So we now need a data structure, a stack or a list of string, for example, or a stack or a list of double. And every time we have a different data type that we want to put into one of our collections, we need to make another class. Right? The only way you can do that in C is to copy your existing code, right? So basically duplicate it, rename your header file and your source code files, rename all your functions, right? And basically duplicate the code that you had from our original implementation. Right? So that's not a very practical way of doing things. Right? So the language C++, which is the, I guess it originated as the object-oriented version of C. It's no longer really that anymore. It's now very much its own thing. Right? So that language has something called templates, where you create a data structure, and that data structure has a parameter, that is the type or types of, that you want to use inside the data structure. When you compile that program, the compiler generates the new copies of all the files for you. Right? So if you had a generic stack in C++, what the compiler does is it takes your source code file, duplicates it, and substitutes in the type for that stack inside the duplicated file. Right? So if you have a stack of int, you get a data structure that's a stack of int. Right? If you say you want to use a stack of double, you get a data structure that's a stack of double. The compiler synthesizes that code for you. And the templating mechanism in C is actually much more sophisticated than that, but that's sufficient for our purposes right now. You know from Java that Java does have generics. And the way it works in Java is you create one class, you make it a generic class, and then you can specify the type that you want to use with that generic class. Right? In Java, you get only one class. Right? So there's only ever one list or stack data structure class. Right? The way it works at runtime is that internally, your list of string is actually a list of big O object. Right? And that works in Java because object is the superclass for all other types, all other reference types in Java. Okay, now C doesn't have that. So C doesn't have this sort of generic mechanism. What C does have, though, is it has this pointer to void. Right? Now remember what a pointer to void can store. It can store the address of anything. Right? So it can store null or the address of any object. Right? And so you can make a generic collection in C if you switch your element type so that it becomes a pointer, a void pointer. Right? So what ends up happening is you end up with a collection that looks like a Python collection, right? Where the programmer can put anything they want into the collection, right? So using this technique, there's no built-in type safety, right? So for example, you can make a stack where you're supposed to be putting ints or pointers to ints onto the stack, but there's nothing stopping you from putting a pointer to a double onto that stack as well. Right? So there's no type safety with this technique, but at least it solves the problem of duplicating your code over and over and over and over again. Right? So like everything else in C, right, the programmer becomes responsible for the types of objects that are added to the collection. Okay, so it turns out you don't have to change very much, at least superficially anyway, to implement a generic collection. So starting with our stack of int, let's change it so that it now becomes a stack of anything. Right? So the structure itself doesn't need to change, right? So our structure, just to remind you what's in our structure, right? So our structure has a pointer to the top node, right? And it has the number of nodes or number of elements in the stack. So nothing there needs to change, right? What does need to change, though, is our node structure. Right? So in our node structure, we're storing an int value as the element. Right? I now need to change that so that it becomes a pointer, a void pointer. Right? So now our node stores a pointer to some value. Oh, wrong one, sorry. Do not do that. Where is the, oh, here it is. Okay, so we need to change our node structure so that it's now pointed to void. Okay, if we go and look at the functions inside of our stack data structure, you'll quickly discover that there are 3 functions that don't need to change because they never actually use the node structure itself. Right, so let's take a look at those quick. So stack init, stack is empty, and stack size. Right, so when we look at stack init, what do? Well, we allocate space for one structure. Right? I set the top node to null. I set the size of the stack to 0, and then I return s. So there's nothing there that actually uses a node, so I don't have to touch init. Is empty looks at the size. I don't have to, so again, not touching a node. Right? And size just looks at the size. So again, not looking at the nodes, so we don't have to change those at all, which is nice. Right? So far, our job looks pretty easy. Right? If you look a little closer at the implementation, you'll discover some of the functions require some small modifications. Right? So push and pop. Push used to take in an integer element to push onto the stack. Now our elements are pointers, right, to something, so they're void pointers. Right? So we have to change that. And pop used to return an int, so now we're going to return a pointer to an element. Notice that the pointer type is void star here. So when you pop a stack, you get back a pointer to void. And so in order to use the object that the pointer is pointing at, you need to know what its type, the programmer needs to remember what its type is. Right? So this is inconvenient, but that's the only way that this works in the language. or it's the only relatively easy way that this works in the language. All right, so let's, if you look at some of the other functions though, you'll quickly discover that there are some very serious problems with this approach. So if I want to print a stack, right, now remember how to print, when we print a stack, previously we knew that the elements were ints. So we know how to print an int. Now if I'm the programmer of the stack data structure and I'm trying to provide a print function, I have no idea how to print the elements because all I'm getting are pointers to void. I don't actually know the element type, right? So let's quickly look at the code again. So print, right? So in print, we print out the element right there, right? The only reason I can do that is because I know the correct conversion here is to convert n-elem to an int, right? If n-elem is a pointer to void, I have no idea what to convert it to. Similarly, with stack free, there's another problem, right? So with stack free, we don't know if the, in stack free, we're going to free the node. So that's not a problem. The problem is does the caller of the function, do they want us to not only free the node, do they want us to free the element that's stored in the node as well, right? Because remember, they're giving us pointers now to the elements, right? So they're not giving us the elements directly. So if they're giving us a pointer to the element, do they want us to deallocate the memory to that element or not, right? Now the problem is, now there's a second problem, right? Even if we assume they want us to deallocate that memory, we have no idea how to deallocate that memory because we don't know what the thing is pointing at, right? So for example, if you made a stack of lists, right, then the way you deallocate a list is you call the list free function, right? You don't say free list, right? Because you might have to deallocate other stuff that's in the structure that you don't know about, right? And so that becomes a problem, right? So there's no way that you can write this function. But there is a solution, fortunately, right? And so if you make the following observation, you might be able to come up with the solution, right? So if I want to print a stack, I need to know how to print the element, right? That's basically what's involved, right? But printing an element, I just need some sort of algorithm to do so, right? Now, as the implementer of the stack, I can't possibly know that algorithm. But whoever made the stack and is pushing elements onto that stack, they know how to print an element, right? So if they're printing ints, they know they can just use printf, a %d, right? If they're pushing strings onto the stack, they know they can just use printf, %s, and so on and so on and so forth, right? Similarly with freeing an element, right? The user of the stack knows what pointers they're pushing onto the stack, right? So they know the objects that they're pushing onto the stack. They know how to free those objects, right? So in C, how do you implement an algorithm? Well, it's just a function, right? And so what we need is some mechanism to pass a function to stack print and stack free, right? And it turns out you can do that, right? So you can pass a function to another function, right? So the way you do that is you pass a pointer to a function, right? And so this is the first time we're seeing a pointer to a function. All right, so in C, you can make a pointer to a function, right? Okay, so in C, a function has a return type, right? It has a name, and then it has a comma-separated list of parameters, where each parameter has a type, right? So if that's your function, right, then a pointer to a function has the following form, right? So if your function has this return type, then your pointer to a function also has that return type, right? If your function has this list of parameters, then your pointer to the function also has that list of parameters. Here the parameters only include the types. You don't care about the names of the parameters, right? Now inside round brackets, you've got the star to indicate that this is actually a pointer, and then finally you have the pointer name. So this is very weird, right? So before when we had pointers, it was star, you'd have, you'd write something like int star p equals something, right? Equals the address of some int, right? Now the pointer name gets buried inside of these round brackets, Right? So the syntax is very odd, and it's really awkward to use until you get used to it. Right? Eventually it becomes natural, or almost natural, right? But until you get used to it, so you have to do this a few times before you actually get used to it. Right? So you want to make a pointer to a function that returns an int. That's int, right? And this is your parameter list, right? The name of your pointer goes here, right? So there's no, so your name of your pointer goes there. All right, so let's look at pointer to func.c. I guess I have to open it up. Okay, so here's my file pointer to function. So I've got a bunch of functions, right? So I have several, so 5 or 6. So here's a function called do nothing, right? Its return type is void, its parameter is void, right? So no parameters. Here's a second function, print int, right? Returns void, has one int parameter. There's max, right? Returns int, has 2 ints as its parameters. There's min, right? Here's make double. So make double returns a pointer, right? Takes in a pointer to a double. And here's another, so let's ignore this one for now, because this is a little too complicated for our purposes. Okay, I would like to make a pointer to the function do nothing. Right? Now remember what your pointer type looks like. It's the same as the function type. It's the same as the function declaration. You just replace the name of the function with round brackets star some name. Right? So my pointer is going to look like void, round bracket, star some name, round bracket, void. So there's my pointer type right there. Right? So that declares both the pointer type and the pointer variable itself. Right? So void, round bracket, star ptr1 void, right, says that ptr1 is a pointer to a function that returns void and has no parameters. Right? Now, what can I assign to that pointer? I can assign I can assign any function that returns void and has void as its parameter. Right? So I can assign the function do nothing to that pointer. Right? You can also, it's also legal to write the address of the function. Right? So you can also write address of do nothing, so that's fine too. Right? But if you don't put the address on, the compiler takes care of that for you. Right? So remember, if I have a second function, so let me insert a second function very quickly. Void something else. We'll just call it do nothing, also nothing. Right? So that literally does nothing. Right? You can then write ptr1, equals also nothing. Like that. Right? So you can make that pointer point to whatever function you want as long as the function has the correct return type and parameter list. If you stop and think about this for a second, you'll quickly realize that this is a very powerful technique in C. Right? So it now becomes possible to call a function by passing in another function. Right? That function that you pass in, you'll pass it in as a pointer, but you know that the pointer that but you are reasonably confident that the pointer that's passed in is a valid pointer. Right? So it's a pointer to a function having the correct types, parameter types and return type. Okay, so let's go back and look at print int. Print int returns void, has one int parameter. Right? So to make a pointer to that function, right, I write the return type, right? I duplicate the parameter list, right? And then I give it a name inside round brackets with a star. Right? So ptr2 is a pointer to a function that returns void and has one int parameter. Right? And now we're in the position to read the rest of them, well, except for the last one. So ptr3, right, is a pointer that points to a function that returns an int and has 2 int parameters. Right? Now we also have min. Right? So min also takes in an int and has 2 int parameters. So if I wanted to, I can assign the address of min or just min. Right? So again, the address of is not needed. You can write that. Right? I can assign the function min to the pointer ptr3. right? If you try to assign a function to a pointer that has the wrong type, the compiler will issue, I believe, an error. So you'll get an error when you try to compile your program. Okay, so what about make double? So make double returns a pointer to a double. Is that right? Returns a pointer to a double, has one double parameter. So if I want to create a pointer to make double, right? Just copy down the return type, right? Copy down the parameter list, and insert the name of the pointer with a star inside round brackets in front of the parameter list. Right? So ptr4 is a pointer to a function that returns a pointer to double and has one double parameter. Okay, so the last function is a bit complicated. So here's make int. Right? So make int is going to dynamically allocate space for one int value. Right? It's then going to store in that in that int object, right, either a or b, or some combination of a or b. Right? Now, what value is it exactly going to store? Well, it's going to call some function involving a and b. Right? So how is it going to call that function? Well, we're going to pass in a pointer to a function that takes in two ints and returns an int. Right? So to call the function from inside your function, right? Oh, sorry, a comma b. Right? Now you say, well, this is a pointer, so if I want to actually use the object that's pointed at, I should dereference it. Right? So you can dereference the pointer like that. Right? And then, whoa, that's a function, so now I can call the function like that. Right? However, the compiler is smart enough to know if you're passing it a pointer to a function, you can just use the function, you can just use the pointer name itself, and that suffices for the function name. Right? So in other words, you could just write that. Right? The compiler will automatically dereference the pointer for you. FP is a pointer to a function. Right? So the compiler will automatically dereference it for you. Now you can call the function. Right? So both of those are fine. Right? And so now whoever's calling make int, they can decide how is it exactly they want to make the int. Right? Do they want to take the min? Do they want to take the max? Do they want to take the sum? Do they want to take the difference? Et cetera, et cetera, et cetera, et cetera. Right? This function will take in any function that operates on two ints and produces an int value. Okay, so down in our main function, if I want a pointer to this function, what do? Well, you just copy the return type, so that's int star. Right? So there's my int star. Right? Now you copy the parameter list. So you come up here and you copy all of this. Right? So that shows up down here. Right? Again, the name of your parameters doesn't matter. Right? So you can leave the a and the b off here. They don't have to be here. Right? In front of the parameter list, round bracket, star, name of the pointer. So ptr5 is a pointer to a function that returns a pointer to an int, takes in an int, and a pointer to a function that returns an int and takes in two ints. Right? I can now assign the address of the function makeInt to that pointer, or you can just write makeInt. Right? That also works. Right? And now I can call the pointer. I can call the function. Right? So using the pointer, I can call the function. Dereference the pointer. That gives you a function. Call the function. Right? Now, the third argument to this function is a pointer to another function. Right? So it's a pointer to a function that takes in two ints, returns an int. ptr3 is exactly one of those pointers. Right? That's cool. It even tells you that. That's neat. Right? So it tells you that ptr3 is in fact a pointer to a function, takes in two ints, returns an int. Right? And if you print out the result here, assuming I comment out this line of code here, right, then this will print 10, the maximum value of 5 and 10. Right? Okay, so that's how you write a pointer to a function. And now that we have pointers to functions, right, we can go ahead and implement our stack, our generic stack data structure. Okay, so if I want to print an element inside stack print, I need a function that can print an element, right? How are elements stored? They're stored as pointers to void, right? So if someone gives me a function that returns void and takes in a pointer to void, that prints the value of that element, right? Then I can pass that pointer, or they can pass this pointer, a pointer to this type of function to stack print, right? Stack print can use that function that's passed into it to call a function, right? This is const void here because printing an element should not change the object that's being printed, right? So it makes sense to declare this as const void star, right? So that means the function that I want, the pointer to a function that I want has the following form, right? It returns void. It takes in one const void star pointer, or one const void pointer, right? And prints the element, right? So I want one of these for stack print. Right? Now, this is, this isn't too bad, right? It's a relatively simple function that this is a pointer to. So it's not terrible writing this. It's also not entirely pleasant to read this. So this is where type defs become useful, right? So instead of using this as my type, right, I can create a type def, right? So my type def for a pointer to a function has the following form, right? So remember how type defs work, right? So it's type def, your actual type, and then your new alias for the type. When it's a pointer to a function, it looks slightly different, right? So your new alias to the type is the name inside of the round brackets, right? So my alias is called print elem func, right? So that's a pointer to a function that can print an element, right? The actual type of that object is a function, so that's what the star inside the round brackets means, right? That returns void and has a const void pointer to an element, right? So there's your type def. So now someone can write print elem func, some pointer name, so p, equals whatever their printing function is called, right? They don't have to write void star p const void star elem equals their pointer, the pointer to their function. Right? They can just write that, which is a lot easier to read and a lot easier to understand. Right? So this is one of the cases where writing a type def is actually useful. Right? Okay, to free an element, right? It's pretty similar. Right? Freeing an element takes in a pointer to void, right? Returns void. Here it's a pointer. It's not const because when you free an element, you are destroying the element, right? So you're changing it. So this can't be const. Right. So for this function here, I want a pointer that has the following form, right? Returns a pointer to a function that returns void, takes in a pointer to void, right? And again, you can create a type def for that, right? So free elem func is just another name for a pointer to a function that returns void and takes in a void pointer as its argument. Right. Okay, if you're going to make these type defs, you have to make these usable or visible to the user. So we're going to put these into our header file. All right, so let's take a look at our generic stack. So this is code, stack, C, and stack. Whoa, no, KH. Okay, so in our header file, right, everything's the same, except now we introduce some type defs, right? So there's my pointer to a function that can print an element, right? Here's a pointer, here's my type def for a pointer that can free an element. But init doesn't change, right? Is empty doesn't change. Size doesn't change. Right? Push changes because now we're going to push an element onto the stack. I guess that can technically be const void elem. That would be fine. Pop returns a pointer to void now. Right? Now print also changes. Right? So print will print a stack, but the only way you can print a stack is if you give it a pointer to a function that it can actually print an element. Right? So there's your pointer type. There's your parameter name. Right? So print elem is a pointer to a function that can print an element. And there's free. Right? So free can free a stack as long as you give it a pointer to a function that can free an element. Right? Now, if the user doesn't want to free the elements that are on the stack, and it's entirely possible that that's the case, right? Then free says that if the pointer is null, right? So if that thing is null, then when we try to free the stack, we're not going to free the elements, right? We'll free the nodes, we'll free the stack structure itself. The storage or the objects representing the elements themselves, they're not freed, right? And that's a perfectly sensible use case for our stack. Okay, so what about the class or the data structure itself? So our nodes are now pointers, right? They now hold pointers to elements, right? And it doesn't change. Is empty doesn't change. Stack doesn't change. Push changes, but there's almost no change whatsoever, right? We're going to push a pointer to an element instead onto the stack, right? So that changes. Nothing else here changes, right? Because nothing else here cares about the element type. Right? Pop also changes very slightly. So when you get the top element, right, that's now a pointer to void. That's now a void pointer, right? And so we're also going to return that element as well. Okay, what about free? Right? So if you want to free all the nodes, notice what pop doesn't do. Right? So pop does not deallocate the memory for the element. Right? Because if someone's popping a stack, they almost certainly want the element that's on top. Right? So yes, we are freeing the node, right? That represented the top node of the stack, but you're not freeing the element that was pointed at in that node, right? Instead, that element is being returned back to the caller. If the caller wants to free it now, they can. Okay, so what about free? So free doesn't really change, except that now you're passing in a function to a pointer that can free an element, right? So, starting at the top node of the stack, or a pointer to the top node, I suppose, right? While that pointer is not null, there is a node, right? Get a pointer to the next node in the sequence so that I can move to the next node in the next step, right? Okay, if this pointer is null, then we're not going to free the elements, right? If it isn't null, we're going to free the element by calling the function, right? So if that pointer is not null, right? Free the element. How do I free the element? Just call the function that's pointed at by free elem, right? You can also call it this way if you like, right? So just free the element. Just call the function, free the element, right? Then free the node, move to the next node, right? Once you're done freeing all the nodes and possibly all the elements, go ahead and free the stack. Go ahead and free the structure representing the stack. Right? And so now we've solved our problem of not knowing how to free an element. Right? We still don't know how to free an element, but somebody can tell us how to free the element. They just have to give us a pointer to a function. Right? Similarly with print, right? Print now takes in a pointer to some function that knows how to print an element. So if I want to print an element, I just call the function, like that. Right? And now, so the changes to the data structure are relatively small, right? That you need to that you need to do in order to produce a data structure that can hold any element type. That's fine. That's just a recursive version of print, but that's not that interesting for our purposes. Right? And so there you have it. So there is a generic version of a stack. Now, there are some issues that you have to worry about when you use this thing. Right? So, problem number one, there's no type safety here. Right? So when someone pushes an element onto that stack, right, all that gets pushed onto the stack is a pointer of unknown type. Right? So it points to an object of unknown type, which means you can push whatever you want onto the stack. Right? You can take any pointer and you can push that onto the stack. Right? And so whoever gets the stack afterwards, when they pop elements from the stack, they have no idea what's there. Right? So whoever's using the stack needs to remember or needs to be careful about what elements they are pushing onto the stack. Right? Almost certainly, they're only going to be pushing a single element type onto the stack. But if they're doing something strange, which is not that unusual, then they have to remember what order they pushed elements onto the stack in. Right? So no type safety. So compared to Java, that's not great. Right? The second problem, right? You're pushing pointers to elements onto the stack, right? And so you have to remember that that pointer needs to be valid at all times, right? So what you can't do is you can't go into a function somewhere, right? Create an int variable, so int I equals 0, right? Push a pointer to that int variable onto the stack, and then leave the function, right? What happens, right? You just push the pointer to a value that no longer exists, right? So after that function returns, the pointer to the int, that int object no longer exists. When someone pops the stack and gets that pointer and tries to use the pointer, everything blows up on them, right? Because they dereference an invalid pointer, right? So you have to remember that when you're using this thing, whatever you're pushing onto the stack must have been dynamically allocated, right? If it wasn't dynamically allocated, then the only place you can do this, the only place you can push and then pop the element off the stack is within the same function. Right? I suppose you could also push static stuff onto the stack. That would be fine too, because their lifetime is the lifetime of the program. So there are some precautions there are some things you have to be aware of when you're using this thing. Right? It's very easy to say, oh, I've got a stack of int. I'm just going to make a temporary int variable and push the pointer to that int variable onto the stack, right? And then later on, your stack explodes because when you dereference that element, it's an invalid pointer. Right? And that's how you make a generic stack in C. You can do the same thing with list, right? So with list, it's almost exactly the same thing, right? Your nodes or your array. If you have an array-based list, you can do the same thing, right? You can make an array a void, right? So make a void, allocate a chunk of memory that can hold a bunch of void pointers, and now you can add whatever elements you want to the list. Right. Okay, so generic data structures are possible in C. Oh, here, I even talk about here, right? So the disadvantages are elements should have allocated storage duration, right? And there's no static type safety. Oh, there's a little demo program here, if you want to see that. So just to illustrate the nonsense you can get up to in C, it's fun to look at this little program. Is it yet? Code. All right, so C as a language is, so the language is very permissive. The compiler will basically trust the programmer, trust that whatever the programmer is writing is what the programmer intends to write, right? So when you're dealing with pointers to void, right, the compiler doesn't care what you try to cast that to, right? So the compiler says, well, look, you've given me this pointer. It points somewhere at something. As a compiler, I don't know what it's pointing at. You're the programmer, you know what it's pointing at, so I'm going to trust you whenever you try to cast this pointer to something. Right? So here's a function print x. It takes in a pointer to some element. Right? The pointer has type void star. Right? So you can get up to the following nonsense here. Right? I can take that element, or that pointer to that element, cast it to a pointer to int. Right? Then I can try to dereference it. Like that. Why did I say it's equal to 1? Right. On the next line, I can take that element, or the pointer to that element, and cast it to car. Right? I think this here is, let me quickly go and look at what I was doing. Up here, yes, okay, so this is inserted for illustration purposes in a previous lecture. So I can take that element, I can cast it to car, right? So when you do that, what the compiler does is it looks at the pointer, right? When you dereference that pointer, it jumps to that memory location. It looks at the 8 bits that are sitting in that memory location and says, well, this is the car value that's sitting in that memory location, right? So I'm going to cast it to car. I'm going to check, is that variable, is that car, right? Is it in fact the H, right? If it's the H, I'm going to print the element, right? Okay, I'm now going to dereference it and see, is that value actually equal to the number 1? Not the printable value 1, the actual value 1, right? Cast it to an int, or cast the pointer to an int, to a pointer to int, and then print the value, right? If it's not the H, right, I'm going to say, well, maybe the thing that's being pointed at is in fact a double, right? So I'm going to cast the pointer to that element to a double, right, and interpret whatever is sitting in memory at that location as a double, right? And the compiler is perfectly happy doing this. Right? So here's my stack now, right? So here's my generic stack, right? I'm going to push 3 elements onto the stack, right? So I'm going to make a string, and I'm going to the string hello. I'm going to make the int value 1, and I'm going to make the double value 2, right? Now I'm going to push these things onto the stack, right? Notice the stack and the compiler doesn't care, right? So I'm going to push str into the stack. That's just a pointer to car, right? So that's a pointer to something, so the stack lets me push that onto the top of the stack, right? There's the address of I, so that's a pointer to something, so I can push that onto the stack. That's the address of D, that's the address of something, so I can push that onto the stack as well, right? Now I'm going to try to print the stack using this printx function, right? And notice here, the problem in printx is printx doesn't know what the types are that it's trying to print. Right? And so that's what all of this nonsense is up here. Printx is trying to guess what are the elements, what is the element type of the thing that it's trying to print. Right? So it tries to guess, is this thing a car? Right? And does it start with the letter H? If it does, let's assume that it's a string that starts with the letter H. Right? If the value is 1, let's assume that it's an int. So cast it to an int, right, and print it as an int. If it's not equal to 1, it's going to try to cast it to a double and print its value out here. If you run this little program, it does in fact print 2.0000001 and hello, right? But it's gross, right? You never want to write a function that looks like this, right? So in other words, you don't want to have to try to guess what that pointer is actually pointing at. Right? Almost certainly you're going to, the guess is not going to work at some point. Right? However, you can in fact try to guess in the C language. Right? When you're converting a pointer to void, the compiler will let you convert it to any pointer type. Notice that when you pop the stack, it's super awkward. Right? So when you pop the stack, you're getting back pointers to void. If you want to use those elements for something, you almost always have to cast it to the correct type, right? And so it is possible to make one of these generic types, but they're a little awkward to use, and you have to be very careful when you use them. All right, so that's it for today's lecture. I guess everybody have a good weekend, and I will see you on Monday.